Hello, my name is Arthur Fuel, and I'm going to review the course project. For the problem described, what type of machine learning approach is needed in a output metric. The data, so I'll go through here in a moment, is a strong fit, highly linear data, so strong fit for regression models. The MSE is kind of the common metric that I started off with. And I kind of anticipated based on the shape of the data that would be the strongest one. And I tried a few other models and found that model was performing the best, as I'll go over here shortly. In terms of the features, I'll actually look for the data as we speak to that just a little bit here. So the first thing I want to do is a little bit of exploratory data analysis. And so we can see a little bit of our summary statistics that we can calculate here. Just looking at the data, I'd like to look at it a little bit more visually. We have some histograms here, a correlation matrix, a few different other things I generated. I'm used to actually doing things in Power BI and SPSS. And in this one, I wanted to challenge myself by trying to figure out how to do it in Python, the pair plot, here where I'm able to kind of see the scatter plots with a hue of targeting my PE. And one of the things that this tells me is, we do have some outliers on these data sets when we look at the comparison, but overall, we have highly clustered, highly linear data. And so with this pair plot, and doing some of the exploratory data analysis, I'm going to head and get started into running some numbers or running some of the different regression models to see how they performed. We did and also on all of these, I went ahead and I did a feature split on 80 and 20. And so if we look here, say at my random forest, this is one I did with the Poisson criterion, but all of them I used a 80-20 split and then I ran a five-fold validation. I did 5 folds on all of them, pretty strong fits just from the initial analysis that I did. So let's go ahead and look at these result comparisons here. So starting with this standard linear regression, it's actually a pretty decent fit for the model here with 0.92 on, well, the mean squared error is 19, which is not especially significant in and of itself, right? We want to look at that as a comparison and relative to the data that we have. And so if we start comparing again across the different models, we start looking at, let's see, the decision tree regression. Well, our mean squared error actually goes up with decision tree, in this case with the default hyperparameter tunings. And we start to move to k-nearest neighbors, and we can see it's down. Support vectors, an outlier because it's not really meant for this type of data, right? We have highly linear data, and this is and support vectors often used where you have a little more problematic data. And but I wanted to throw that in there just to for good measure. As we start to get into random forest, I actually went deeper with random forest because that one is really showing the best by a good margin on my initial test. We see the mean square, my initial random forest regression at 10.2, and so that kind of gives us an idea of how our models compare, looking at the mean squared error. And of course, now the mean and the standard deviation that we see here, we're actually looking at, this is the mean for the k-fold analysis. And so we can see here that we have pretty strong fit from the get-go in terms of how capable this model is at predicting future data trends. And it's pretty small standard deviation, so pretty clean data set. I mean, very, the data set's very strong fit for linear regression models. But we can see here, just looking at mean squared error for our initial evaluations, it kind of really helped us to kind of narrow in pretty quickly to look at this random forest. And so as we started I did that initial criteria, the initial evaluation to kind of, and then want to dive in deeper on random forest since it looks a little bit more promising than the other models. And so ran another random forest. This time I upped the left the criterion is squared error, but I upped the number of trees in our forest here to 200 to see how big of a difference that made for us here. And so we said with the standard number of trees, which I believe is 100, we were getting our absolute error of 2.35, a squared error of 10.24, and this one's 2.336 and 10.14. And so we are actually, give a fairly meaningful improvement in, and a lot of this, really kind of depends on our business criteria, how much money that we want to invest in the model. Because you imagine if you're using a tree depth of 200, there's going to be or not a depth, but a quantity of trees of 200. An increase in your computational costs for it's not, I didn't actually evaluate the exact computational cost. It wasn't a noticeable delay difference when I did this manually, but there's definitely going to be a computational cost increase with that. And so depending on your business criteria for the model, and we start to look at additional real world evaluation of the model and how much these smaller errors actually make a real world difference for what we do with the data. It may or may not make sense to bump those estimators, but we do see that does give us increase in performance. And in terms of our model fit here, our higher mean is better here. So we've got 9588. And on the next one, we have 9585. So we do actually have a little bit more of an overfit here, though, as we do the estimators. And so this will be not quite as good at predicting data outside of our test set with accuracy there. But standard deviation across these is comparable, slightly lower in the MSE. And so that's an interesting question. I think to determine what's it seems to be a fairly trivial error, but again, there's some things where you're in seconds, and some things you're into billions and trillions of seconds where your meaningful values matter. Or I use seconds as an example there, but it really could be any of the above, or any type of numerical example. And so then the next one, I wanted to try changing some of our models criterion. And so I ran a random forest with absolute error as the criterion for the model. And one of the things that I was a bit surprised about is there is substantially longer to run the computation using MAE as the criteria. And so I didn't do any type of formal analysis of the computational cost, but it was 5, 6, 10 times longer to wait for the results on the so just a quick feel for that is the MAE definitely gonna have a higher computational cost. It's that can depend on the GPUs and stuff, which server farms and all that, but that's my initial evaluation. That's where my nose is leading me, and we can see here compared to let's say right now I'm going to say that this one here, I'm going to assume that this slight overfit is not going to have a significant difference on it compared to the. We're gonna lean with this one. We got our model fit to the curve is a little bit better on the data that we have. So we'll have to try that again with additional with larger volumes of data in the future to see how much that plays out more. But for now, it seems to me that this is the best fitting model. So if I compare these two, right, I can see that my total absolute error goes up, my mean squared error goes up, my mean 9580 down here, and I am 9585 up here. So the higher number here again on that mean for the k-folds is better. So my ability to predict future data is still going to be higher on those, and the standard deviation 0.0026 versus 0.0025. So yeah, everything about and that is true as well for the standard number of estimators as well, is really showing me it's better with the mean squared error. We also ran with the Friedman, which helps to correct for bias and variance. But with the Friedman, let's see, we got compared 2.33, 2.34. So our mean absolute error is higher, our mean squared error is higher, and our but yeah, at the same time, this isn't exactly a fair comparison, right? Because I'm comparing it against the one here that I did the 200 estimator. So if I compare my Friedman to my to my standard forced regression, so 2.35 or 2.34. So it is a little bit better there, and we have 10.24 versus 10.21. So the Friedman is actually a little bit better with the same amount of errors there, and the model fit 9582 to 9588. We have a little bit better predictability, a little better for our standard, probably not a substantial difference there, but it is something. And so it'd be interesting to run this Friedman test with the estimators at 200. But the only reasons why I didn't is before I did that, I wanted to run the Poisson, and the Poisson showed better than the Friedman. Really, for 100 estimators, it actually showed a lower mean squared error. So the Poisson was looking, if 100 estimators is good, then if that's the value we want to run with, Poisson appears to be the strongest model. But it's kind of telling when you bump the estimators to 200 with Poisson, because now we can see that we're actually deteriorating with increased estimators, which is and I think part of the explanation that can be if we start to look at the fit of the data at 9585 versus 9587. So we're starting to overfit. So in the case of Poisson, so when we use the standard mean squared error, right, our estimators actually improved us on most things. It did overfit bump slightly, but it looks like that the same increase in trees impacted the Poisson model a little bit more, which would make me question if we moved. I'd like to see that on a larger data set, even if we were doing the lower volume of estimators, to see if with a larger data set the Poisson would continue that kind of overfit trend and deteriorate more if we went up. So it's we have a really linear data set here. We have a number of the different regression models are fitting very, very nicely, and we're really getting to very, very close criteria on what we think is gonna work best here. But my gut's telling me I would need to do more tests if this was going to be a very significant business metric that we're evaluating with this. But my gut is telling me that the standard MSE based random forest regression with 200 estimators of the different analyses that I've run, this is the one that I would lean towards. If I had to go, move forward with something, if it was not a substantially important business decision, we just need something, this to me is looking the strongest now. Likewise, if this is a more serious business problem, we needed to actually put a little more thought, run some of these through some more different computation, try some more hyperparameter tuning with both with the standard MSE, the Friedman, and the Poisson, to see if additional tuning would flush out one of these as having a more significant prediction value than the others with over time and with more data and more new data. And I think if we did we looked at the features, We did the data split, talked about how I did the data split, talked about how we looked at several different models and where we look at the performance of the final model here. And I believe that's all that's required for the assignment. So thank you for reviewing this. I appreciate your time.